Okay, let's take a look at this. We're going to continue with conversion here. So notice what I have is an example of a rectangular coordinates equation. Actually, it's a relation. Do you guys know what I'm talking about when I say it's a relation? What is this the equation of? Everybody know what this is? This is the equation of a circle. Center is at the origin, and your radius is actually 2. So if you studied conic sections in intermediate algebra or pre-calculus, you already know from the start that this here, if I had to graph this, superimpose my x and y Cartesian coordinate axes, right? This is my x-axis, my y-axis. I'll essentially get a circle of radius 2, and you're kind of looking at it right here. Let me kind of sketch this for you. That would be centered at the origin, okay? And that would have a radius value of 2. And that's a Cartesian coordinate rectangular sort of coordinate system equation. It's really a relation. You guys know the difference. A relation is the difference between a relation and a function. One thing you could do is use the vertical line test. Okay, vertical line test says if you hit that curve in 2 spots, or at least not one, then that's actually a relation. It's not a function technically. I just want to remind you guys of these details. However, that's not what we're going to study necessarily. What we're going to study is still conversion. So the question is going to be, this is a Cartesian coordinates version or function relation. What we want to know now is, what's the polar equation? Can I describe the circle in terms of a polar equation? You know, really R as a function of theta or a relation, okay? So that's kind of what we're looking at. And this is where we're at. So it's still conversion, but we're now converting from one system to another, the Cartesian coordinate functions and graphs to your polar versions. And we're just going to use here the tools we talked about last time. You're going to use the fact that x is described as r cosine theta. And you're going to use the fact that y is r sine theta. So if you remember last time, we converted points using these formulas. We're going to use them again. But this time, we're going to plug in here for x. Notice this. There's an x here. We're going to plug in this value for x, or this relationship. Over here, we have a y. We're going to use this y. So what that means for us is we'll say, replace this x with r cosine theta, and replace the y with what? R sine theta. Okay, so far so good? Now algebraically, what you obtain is this r cosine theta to the second power plus this r sine theta to the second power, and that better equal the value 4. So using algebra, you get r squared cosine squared theta plus r squared sine squared theta, and you have 4. So you're simply able to factor out the r squared. You get cosine squared theta plus sine squared theta, and that equals 4. And you just have to tell me how you recognize this identity anywhere. What's cosine squared theta plus sine squared theta? 1. Good. So now you say we have r squared equals 4. So I'm going to remind you here, by the square root formula, that means r is plus or minus the square root of 4, or r is plus or minus 2. So what this means here is the following. That any time you have r equals a constant value, okay, I'll write that here. R is a constant. It doesn't matter if this is negative or positive. If it's 0, it's trivial. We'll talk about what that means. So we're going to say R is not 0. But what you're looking at here is the equation of a circle centered at the origin or at the pole with a radius of 2. So if you ever say the statement r equals 2 here, and you do, positive 2, automatically go back to the circle and know, my radius here is really what? 2. I'm centered about the origin or the pole. That's analogous to looking at the Cartesian version and saying x squared plus y squared is 4. R is my radius here. My radius is 2 for any arbitrary theta value, any angle. Any theta, here's an angle, my radius is what? 2. Here's another angle over here, my radius is what? 2. Radius is 2, radius is 2, radius is 2, radius is 2. All day long, 2 here is that distance for every angle, which you sketch out is a circle of radius 2 centered at the pole or the origin. Now, notice something interesting as well. It's not just positive 2. If you see the statement, r is negative 2. If r is a negative number, it works the same way. It's just all the radiuses are opposite of these 2's on the other side. So you still get a circle, okay? So I can say to you as well that if my radius here also is negative 2, any theta, we get the exact same circle. So I want to point this out to you that this is a very big deal, especially when you start taking, a calculus course like a calculus 2. We deal with this all the time. What I want to summarize for you guys really is this fact that you have this kind of relationship that R sometimes we say is A not being 0. This is the polar version of a circle. Radius is A, and it's centered at the pole or origin. So anytime you see this, you know what this actually means. It's a circle. So I can say, by the way, our note in your life, if they ever said to graph the polar curve, it'll come. Or let's say equals 9. What do you guys know that really is? This is a what? A circle. And what's your radius going to be? What's the radius of that circle? Anybody know what that radius is? Radius is 9. Okay, centered at the what? At the pole. So that'll come in our future. But I just want to know here to show you that we converted this Cartesian, conic section to polar. And this is a lot easier to deal with, r being a constant value. So let's look at another example and say to you, what if they wanted you to convert this, and it's, let's give you another Cartesian. X squared plus y squared here now is, let's say, 16. You already know that's a circle centered at the origin. What's the radius? 4. Good. You guys taking that Math 260 course? Centered at your origin, it's a circle. Radius is 4. This is what you'd use in those courses. Replace x now with what? R cosine theta. Replace y with r sine theta. So you'll get r cosine theta squared plus r sine theta squared is 16. Continue with our algebra, r squared cosine squared theta plus r squared sine squared theta is 16. Factor out the r squared. You get cosine squared theta plus sine squared theta is 16. What do I know about this? This is 1. And so I have r squared going to be 16, which means r will be plus or minus square root of 16. Square root formula. And r will be plus or minus 4. So if I have the polar equation of r is 4, or if I have the polar equation of r is minus 4, what we know is that these will be circles. Radius 4 centered where? At the pole or at the origin. Just like the Cartesian version. So we're converting Cartesian equations, functions, relations to polar. And you'll find in your future that it's a lot easier to graph that kind of equation. I mean, don't you think just looking at it, r equals a constant, isn't that easier to kind of comprehend? So very often, it's actually much easier to go to polar and to maybe graph or even do some, calculus in your future than it is Cartesian. And that's the idea, and that's really why this polar version, why you study really the polar version. It makes your computation a lot easier. Okay, so these are circles. What's also important for us is lines. So you guys already know this is the graph of y equals x. So if I were to show you here, let's again paste another one of these. You already essentially know what this looks like from algebra. Got my x-axis, my y-axis. What this looks like is the following. This is the line y equals x. Okay? But we're going to ask you, what's the polar representation? So start with y is x. Okay, we know y is x. What else do we know about these variables? What do I replace the y with? R, bless you, sine theta. What do I replace x with? R cosine theta. So you have the equation r sine theta is r cosine theta. Okay, you guys okay with that? Now at this point you might say to me, what do I do with this? Well, let's think about this. Usually you probably want to solve for r, usually, if you can. But what do you guys see as a problem? You can't really solve for r, can you? I don't know, maybe. Let's try to see if we can solve for r. What happens if I translate that term? I get r sine theta minus r cosine theta is 0. If you factor your r out, we get what? Sine theta minus cosine theta is 0. Zero product rule says what? R is 0. And I get sine theta minus cosine theta is 0. I know what this means. This means that sine theta is cosine theta. I did my homework from the last section, and that really means that tangent theta is 1. So I have these two ideas. Now, let's stop and think. We already know what this graph is. What is this graph? Anyone want to tell me what this graph is? This is a line from Cartesian. We already know what it is. It's right here. We know the graph. This is the graph here. Okay? All right, whatever. But what does r equals 0 actually mean? You know what that really means if r is 0? R is 0. Theta is arbitrary. You can have any theta value. And what do you think we're talking about if we have any theta value? You're talking about really this point right here. The origin or the pole. Okay? Now, that's kind of a trivial solution. Some of you might have said to me earlier, you might have remarked, you might have said, okay, let's divide both sides now by r. Yes, r goes away. You're still left with this sine theta equals cosine theta business. We still have tangent theta being 1. We've seen this in our past. What I'm going to say to you guys is focus on this relationship that tangent theta is 1. Now, what this means here, since tangent theta is 1, you can solve for theta. that means theta is two values. What is theta? Theta is pi over 4. What else? What's the other solution for theta? 5 pi over 4. Okay? So if we go back to the graph, and here's the moral of the story. This means theta here, this is my theta, it's pi over 4. And so since I have a value for theta being pi over 4, and I don't have an r value, my radius is what? Arbitrary, meaning I could use any radius value as long as my theta is pi over 4. What that means is, remember, every value here, if I take this polar axis, right, we rotate it by pi over 4, counterclockwise, every value for r in red here is positive. So you can say, oh, here's a positive radius of maybe 1, 2, 3, 4, 5, and 6, and 7. I'm generating points on that blue line. Meaning, as long as theta is pi over 4, I could use any radius value, even negative values, negative 1, negative 2, negative 3, negative 4, negative 5, and so on. I'm generating points all along this what? This line in blue. And all I'm keeping constant is my angle theta being pi over 4. So what I can say to you is, algebraically, the line created by this y equals x, right up here. In polar, that's simply the equation theta is pi over 4. And you might ask me, what about the other value, 5 pi over 4? Well, if it's 5 pi over 4, notice the same thing. You essentially get the same line. And you might say, well, why is that? Because now, if I rotate this 5 pi over 4, here is my, let's erase this. Here's my rotated 5 pi over 4. Here's my angle. Every point on this purple region is positive. Every point over here opposite is negative, I should say. So I have all my negative radius values over here in red. You generate the same line because, yet again, we're going to say any r value. Now this time, theta is 5 pi over 4. So you're going to generate, again, the same exact line that we have here in blue. Either your angle is pi over 4 or 5 pi over 4. The point being, that corresponds to your equation here, or I should say the graph in polar being just a line. And more importantly, we'll give you this fact here. Right? If theta is a constant, doesn't matter what it is. The graph is a what? Is a line through the origin or through the pole. So these two ideas are very big in polar form, very big in trig, very big in calculus too. That r being a constant gives you circles. Theta being a constant gives you what? Lines. And that's what you always want to remember. And you'll see that again in calculus too, that theta being a constant gives you these lines. They're not the only lines that exist in polar, but they're lines that go through the pole or the origin, and they become a factor later on. So I want to start off this kind of discussion just by talking about circles and lines, but by all means, there's not just circles and lines in polar. There's very many other curves that we'll study. But this is our first part. We're just going to convert now from rectangular to what? To polar. Okay? So let's look at another situation here. Maybe you guys know. How about this? Anybody know what this is? Y equals x squared. You guys ever see that before? Probably. Isn't this a parabola through the origin? Okay, so let's replace some things here. See what you guys think. What am I going to replace y with if I convert to polar? R sine theta. Good. What about this x squared? R cosine theta. So algebraically, I have r sine theta is r cosine theta squared. R sine theta is r squared cosine squared theta. Now I can do the same thing again like I did before. I can translate this term. So I get r squared cosine squared theta minus r sine theta is 0. Factor the r out, I get r. What do I get? Yeah, factor r out, you get what? R cosine squared theta minus just sine theta. And this is 0. Zero product rule. R is 0. The pole again. R cosine squared theta minus sine theta is 0. Okay, what do you guys think? What do I do now? Can I solve for r? Remember, very often, what do we want to do? Solve for r. We did here. That gives me my pole. Okay, again, somewhat trivial, but okay. Let's solve for r here. R cosine squared theta is sine theta, and r here will be sine theta over cosine squared theta. R is sine theta. What's the reciprocal of cosine squared? Anybody know? Why don't we just say, isn't this going to be what? Maybe secant theta squared? And so I think we can say sine theta times, how about if we try it this way? Let's do it a little different. We don't have to say secant theta. Why don't we just say 1 over cosine squared theta? And so r is going to be sine theta times 1 over cosine theta times 1 over cosine theta. So r becomes sine over cosine times secant theta. You know what sine over cosine is? That's tangent theta, secant theta. So this equation here, r is tangent theta, secant theta, this is our polar equation for y equals what? X squared. This is your parabola. You know, so if you had to graph this, maybe. All right, we had to graph this. Here's my x-axis. Here's the y-axis. You know, you get something that looks like this. And this is in polar. Well, r equals tangent theta, secant theta. Okay, notice the pole here. We say you have that pole here. Notice the pole is actually plotted on this what? Graph. Anyway, let's see some more. We got circles, we got lines. Let's say, for example, let's go through another general equation. What was the general equation of a line? Do you guys know? Standard form, ax plus by is actually c. This is a standard form of a line. And we can convert this to polar. Same way. You're going to have x be r cosine theta, y be r sine theta. Algebraically, ar cosine theta plus what? br sine theta is c. Factor your r out. What do you get? A cosine theta plus b sine theta is c. Divide both sides now by A cosine theta plus B sine theta. A cosine theta plus B sine theta. We get cancellation, and my R value equals C over A cosine theta plus B sine theta. So this is your general equation of a line in polar. Notice we write R as a function of theta. So we have these lines, we got these circles. Let's look at another line here really quick. Another example. They could give us something like this. Y is x minus 3. Let's see what this becomes, and let's convert this. Right? Y will be R, what's that? Sine theta or cosine theta? Okay. What is x? R cosine theta. So we have R sine theta is R cosine theta minus 3. So solve for R. Can translate and say R sine theta minus R cosine theta is negative 3. Factor out your R. Divide both sides now by your sine theta minus cosine theta, just using algebra. And now you get R. R being negative 3 over that sine theta minus cosine theta. And then don't be disturbed if you look in back of the book, you get positive 3 here. You get cosine theta minus sine theta. Here's your polar version of the y equals x minus 3 in polar. So we're converting to polar. So all of these representations will work in polar. Does anybody remember what this might be? What's this going to be? Let's try this. X squared minus y squared is 1. Anybody know what this is? It's a hyperbola, good. So we have hyperbolas described in polar form. Same thing, replace your x with r cosine theta, replace y with r sine theta. So notice you have r squared cosine squared theta minus r squared sine squared theta, and that is 1. Now remember, we're solving for r, right? Or r squared. Either. If you factor out r squared here, you get cosine squared theta minus sine squared theta. This is 1. And now you're going to divide both sides again by the cosine squared theta minus sine squared theta. Cosine squared theta minus the sine squared theta. So here's what we get. We get your r squared being 1 over cosine squared theta minus my sine squared theta. And so I'm going to ask you guys to hopefully recognize something here. What is this equivalent to? Is that 1? Say no. That's a big no. That's not cosine squared theta plus sine squared theta. That's cosine squared theta minus sine squared theta. Anybody know what that is? That's an identity. You got to know this identity. What is it? What's the identity? What do you guys think? You got to know this identity. Isn't this cosine 2 theta? You might have proved it on your last test. Why do you think I make you guys prove those? So you can remember them. So r squared will be 1 over cosine 2 theta. You can see it this way, and you can also see it what other way? Yes. R squared is secant 2 theta. So this here, if you guys remember your equation of your hyperbola, it's actually, if I remember, a horizontal hyperbola. Is that true? So put that in red, horizontal, because you have two types. You got a vertical, you got a what? Horizontal hyperbola. So remember those things, and this is your polar version of that equation. Okay, so it's not really, like I said, it's you can have r, you can have r squared, solve for those two variables. Sometimes you don't have an r, you just have a theta. If that's the case, you know it's a line, and you know that's what you're looking at. But you have other graphs to consider. But essentially, this is kind of what you're looking at so far. Okay, so I'm going to give you guys a start here with this, and now let's start to do the opposite. Do you guys know what's the opposite? What if, for example, I'm going to write down this fact or this phrase here, right? We can convert from polar to what? Rectangular. So we're going to do this all in reverse now. From polar to what? Rectangular. Okay, you guys okay with that? Yes.
I have a question for the last one we did. Do we just leave r squared like that?
Yes.
Why?
It's kind of like just like having x squared or y squared, like you're looking at r squared or r is really what you want to solve for. Now, if you said, okay, I want to have the square root there or something, and you're making this a little bit more complicated than it has to be. But I understand why you'd ask that, because you haven't seen how to graph things with r squared yet. That comes a little later. But you can graph things with r squared and graph things with r. So you want to solve for r squared. So the short answer to your question is, yeah, that's perfectly fine. R squared is okay, as long as it's just r squared and there's no other r's really, I think, anywhere. But it kind of goes back to you graphing other things in your life or looking at relations. You know, when you had Cartesian coordinates, you didn't have always, you know, y. You might have had y squared. And maybe you're saying to me, this is what I kind of mean by that. You know, you can graph y squared as 4x. Now, you don't do this in intermediate algebra. You do it in what? Pre-calculus. So some of you guys have actually done these graphs here in pre-calculus. Anybody here taking pre-calculus? Have you ever graphed anything like that? What's this graph? Where's the pre-calculus students? This is, again, it's sort of a parabola, but it's on its side. Is that right? It's opening either to the x-axis, positive x-axis, or positive y-axis. So you have seen things that look like that, is what I'm saying. So I don't know if that kind of makes any sense to you. But that's happening also in polar, just to say that. So if you have r squared, that's perfectly fine. You don't have to take the square root. But let's go back now. Let's convert from what? We're going to be given a polar curve now. And we have to find what that is rectangular. So for example, they may say you got r cosine theta is 4. And note, they can say r is 4 secant theta. I just want to put that down there for you guys. R is 4 secant theta is the same as what you guys see over here. Is that true? By saying r cosine theta is 4? So even if they gave you r is 4 secant theta, you could do the algebra, because you can say, oh, I know. Secant theta is 1 over what? Cosine. So this is r is 4 over cosine. I can multiply both sides by cosine. And notice I get r cosine theta is 4. I just want to point that out to you. They didn't give it to you as r equals, and they don't have to. Now, the reason they didn't do that, does anybody know why they didn't do this? Why didn't they give us this original question this way? The way I described you here. R is 4 secant theta. Because in the beginning here for this example, I believe they want you to recognize one thing. What is R cosine theta? What is this portion right here? That's right. So this is simply what? X is 4. Have you guys taken beginning algebra? Or pre-algebra? What is this? What does this represent? This again is a line. Okay. What about that line? Horizontal or vertical? It's a vertical line. Goes to the value X is 4. You know, so if you said to me the following, you said, wait a minute, do you mean to tell me all I have to do is find where X is 4, 1, 2, 3, 4, right here, X is 4, and I can draw a vertical line here. Remember, this here is your imaginary Cartesian coordinate. X-axis, y-axis. We're describing this line right here. But the polar representation happens to be R is 4 what? Secant theta. So you're going to from both worlds, you know, from polar to rectangular, from rectangular to polar. And again, the idea really is, and it may not be something that at this point for some of you guys you think, you know what, this is a simpler representation. You're right, it is. That is much simpler than what? R is 4 secant theta. But we're going back and forth because of the fact that in some cases it's easier to do things in rectangular coordinates, and in other cases it's a lot easier to do things in what? Polar coordinates. And it might not be so clear at this point for you guys because you're not taking some of those other classes yet. But this is a very big deal, you know, going from one system to the other. And it makes some of the work that you do a lot easier. And we're going to see some of that in terms of the graphing, just so you guys know. But we still want to, you know, get sort of, familiar with these kind of graphs. And so we're going to spend some time with it, but that's kind of what this really means for us. Similarly, if they give you R, sine theta maybe is -2. What they want you to know or to recognize at first is right here. See R sine theta? What's that? That's y. So you can say, oh, they mean y is -2. Now say to you, yeah, y is -2. So if I go back to the prior graph here, and we had to really graph this, -2 for y would be 1, 2, right here. This is, if you guys remember from beginning algebra, what kind of line is this? It's a horizontal line. Let's get rid of this other madness. So from beginning algebra, this is a line, y is -2. But in the polar world, we can say r sine theta is -2. Yes, it's easier to describe this as y is -2. Some cases, again, rectangular coordinates are easier to describe things. Other cases, it's polar. So let's get rid of this here and say this is the line y is -2. This is not what we're looking at anymore. That was a prior example. And that's really describing this rectangular. By the way, another note. They could have said R here is -2, oh what? Cosecant theta. Is that true? Is that the same equation? Say yes. So if they would have given you this to begin with, R is -2 cosecant theta, and you go, oh my God, what is this, right? God, that what looks scary. What is this in rectangular? Well, you replace the cosecant theta with the reciprocal of what? 1 over sine theta. So now you have y is -2 over that sine theta. Multiply both sides by sine theta, and you get y. Where's r? Sorry. You get the r sine theta is -2 equation. So I just want to point out to you, oh, wait a minute. What are we doing? Yeah, that's the same equation. Just want to point out to you they're equivalent. But in the beginning, they just want you to recognize r sine theta and r cosine theta wherever you see it. So wherever you see it, replace it with an x or a y. And that's kind of the exercise, really. So I think it's less intimidating for people if they start to see it that way, at first. But let's look at some more. So what do you guys think? Is this okay? Compare these examples, by the way. See what you think of this. Compare these examples here to r is 4 cosine theta. This is different. Is that different than what you were given in the prior two? Notice this. This is r cosine theta is 4. This is 4 cosine theta is r. So here's what you guys are going to do here. Okay? You're going to multiply both sides here by r. Okay? And what you now get is r squared on the left, and I'm going to rewrite this product as 4r cosine theta. Why do you think I rewrote it as 4r cosine theta? Do you see an r cosine theta anywhere? You do? I do. What do I replace it with? Good. This portion is x. What do you think my r squared will be? R squared. X squared plus y squared. X squared plus y squared is 4x. This is a Cartesian coordinate, I should say, relation. It's not a function, it's a relation. We got x squared plus y squared is 4x. There's no r, there's no theta. But if I ask you guys a question here, and what will happen in the future is this. Let me erase what we really did. In the future, they're going to say to you to graph this curve. R equals 4 cosine theta. Now, it's important for you guys to know what that graph is. So what I'm saying now is, if you see this relation, what is this? Anybody ever see anything like that before? Yes.
How did you get x squared and y squared?
It goes back to this here, r squared. What's r squared equal to? It is x squared plus what? Y squared. Remember that from yesterday? Pythagorean theorem? Yes. So that's another thing you want to recognize. You want to recognize all of those relationships, those 4 relationships yesterday. R squared is x squared plus y squared. What's tangent? Y over what? X. Good. Tangent theta, to be exact. Back to this. Anybody here taking pre-calculus? Huh? What is this? I want to tell you guys, it's a circle. And you might say to me, it's a circle. It sure is. How do I know? Does anybody ever remember this process called complete the what? The square. If you don't, good news. You study complete the square in Math 260 and Math 125. Pre-calculus and intermediate algebra. That's where we study complete the square. I even have a video on my Math 125 website on complete the square. Anybody remember how to do this? What do you guys do? X squared plus y squared is what? 4x. Let's try to do this really quick. Translate the 4x, because it's not a video on complete the square, right? So we have x squared plus y squared minus 4x. That equals 0. Complete the square, I'm going to rewrite this because my linear term is in terms of the variable x. So I really have to complete the square in this example in terms of the x what? Variable. This number here, that's my b value. So remember, complete the square. You're going to take half of that b value. Half of negative 4 is negative 2. And use that value. Second step will be to take negative 2 and square it, and you get what? Positive 4. So let's remind you here of what you do in complete the square. X squared minus 4x, y squared equals 0. Remember what you guys do with complete the square? I'm going to add what? The 4 to both sides. I always add this value here to both sides. That's what I do. And then what you'll do here, you got a perfect square trinomial here. You factor. But if you are really familiar with this technique, you don't really have to what? Factor. It'll be x to the power 2 plus y squared, and 0 plus 4 is 4. What you do now, I'll put this in purple. The number you get here, negative 2, gets placed where? All the way over here. Negative 2. So I always say factor, you really don't. And what you're looking at here now is this equation that x minus 2 in parentheses squared plus y squared is 4. Just in case you guys have forgotten, this is the equation of a circle. Where's the center of this circle at? X is 2, y is 0. What's the radius of this circle? 2. So, to make a long story short, yes, you did convert by going from this step here. R equals cosine theta to this equation to this equation. You've converted. X squared plus y squared is 4x. Now that's a conversion. That's perfectly allowed. And if you gave that as an answer, I would say fine, that's good. But later on, when they say to graph this, this isn't good enough to what? To graph. Do you guys agree? So let's say it again, because sometimes people have to hear that twice. If it's just to convert, we're done right here. If it's to graph now, you got to know what you're looking at. You got to complete the square, and now you're able to do what? To graph this. Is that true? Let me show you what I mean. This circle is centered at what? 2, 0. Right here. This is on the x-axis, right? Oh, sorry. Sorry, we're wrong. This is on what axis again? So we'd have to go 2, 0. 1, 2, right here. That's the center of my circle. What's the radius? 2. So you'd have to go up 2, to the right 2, to the left 2, and then you get to sketch your circle. Okay? Rough sketch. Very rough sketch. It's not a circle, it's like a bad egg omelet or something, right? Let's erase this center. That's my point. You'd have to graph this later on, or in Calculus 2 or later on, tomorrow or the next day. But you're done converting just looking at this right up here. Okay? Just want to point this out. Eventually you'll have to complete the square if you're going to graph. Let's go to the next example. You got a similar example here. They give you r is 4 cosine theta. What if they gave you r is actually 6, sine theta? what you're going to do now, similarly, is multiply the left side and the right side now by what? By r. You get r squared will be 6r sine theta. Now they gave this to you because hopefully you're going to recognize what this is right here. What is this? Let's change the color. What's r sine theta and what's r squared? You guys want to tell me what r sine theta is? Good. What's r squared? Good. So we get x squared plus y squared becomes 6y. Did you convert to rectangular? The answer is what? Yes. But they may say, what is this? Well, it's a circle. And you might have to go to the details. So let's go through some details again, completing the square, because it probably is worth doing. I won't take my time, but I'll show you this is x squared plus y squared plus 6y is 0. We got to complete the square with the variable x or y. It'll be y, because we have a linear y term. Okay, so x squared plus, let's go back, y squared, plus 6y. Remember, this is 0. Believe it or not, I'm going to do what? I'm going to take half of 6, which is 3, and then I'll square that 3, and I get 9. Plus 9. Plus 9. Oh, you're right. It's a minus. Thank you. Glad you're awake. It will be. And that'll change, really, our answer. Okay. We're still adding and subtracting 9, okay? Now, remember, what do we do here? We're going to complete the square over, or I'm sorry, factor your perfect square trinomial. So you now get your x squared plus, this is where it'll make a difference. Y minus 3 squared is 9. So you do have a circle again. Okay, equation of your circle. Center is at 0 now, positive 3, and then the radius is 3. So yes, we did convert. If you just asked to convert, you're done there. But if you're going to have to graph, you're going to have to know what kind of circle that is. Okay, so this is converting now from polar to rectangular, and it's always good for us to know how to do that and what we're looking at. Okay, let's give you guys another question here. What if they gave us r squared is tangent theta? Okay, we got to convert to what? From polar to rectangular. So, can you tell me, by the way, what do I replace tangent theta with? What is it? Y over x? Okay. And what do I replace r squared with? X squared plus y squared? Okay. What do I get? X squared plus y squared becomes y over x. Okay, let's double check here. There you go. Let's look at another example. How about this one? R squared is sine 2 theta. We're just going to convert these here. What do we replace r squared with? X squared plus y squared. What do we actually replace sine, what do we replace sine 2 theta with? Anybody know? Sine 2 theta, what could we replace that with? Is there a nice identity? 2 sine theta cosine theta, is that right? Let's put this together. We're only converting here. If I ask you guys this question, are we done? Say no. Anybody know why? Why aren't we done with this? Just converting. If you're going to describe this in terms of x and y only rectangular coordinates, you're going to have to get rid of your sine theta, cosine theta. Is that right? Okay. Let me show you how you can do that. Anybody have an idea what we could do? Let me multiply by r to both sides. In fact, let's let it be r squared. And you might say, well, what does that do for me? Well, you get really r squared, which is x squared plus y squared, times another x squared plus y squared on the left side. On that left side, you're simply going to get x squared plus y squared to the second power. Does everybody agree with that? Multiply both sides by r squared. Now you might say, why did you do that? So I can get 2, this will be now r sine theta times r what? Cosine theta. You see the r squared here is r times r. Now why is that a nice thing to do? Anybody want to tell me? What is this r sine theta? What's r cosine theta? Y and what? X. So this is going to be simply 2x what? Y. All right, you guys okay with this? This here is a Cartesian coordinate equation. Really a relation. It's in terms of x and y, and your polar form was above. Okay, you guys okay with these? So we did some conversion. Now I have some more I can do. I don't know if you guys want to do some more. You want to try one more, or what do you want to do? You want to try one more, or you want me to do them all for you on video? Should we try one more, or should I just do the rest on video? Do the rest on video. Oh, okay. All right, I will. Okay, we're going to continue here with the problems that we said earlier in class. We're going to continue converting. We're going to give some more examples here. So let's start again here with this r equals 1 over, I believe that's 1 plus sine theta. Okay? So let's see what we're going to do here with this. Let me write this down. R is 1 over 1 plus sine theta. I'm going to multiply both top and bottom by 1 plus sine theta. So this is 1 plus sine theta. Now on the right side, we'll end up with r times 1 plus sine theta, or we can put this, I guess we have what? 1 plus sine theta times r, and I get cancellation here. I'll get 1. Okay? So here's what I'm going to try now, I guess. Let's see. I can multiply now both sides here by r. I could distribute this r. So I'll get r plus r sine theta equals 1. And I can say that r then, if I translate this term, I get r then will be 1 minus r sine theta. So I can recognize what I have here. Okay, r sine theta, let me undo that. This r sine theta we can actually replace with y. And so algebraically, we have r equal to 1 minus y. Okay. So I can say here now, we can square both sides here. So you get r squared is really 1 minus y squared. And I can replace now this r squared here with what it's equivalent to. And that's simply x squared plus y squared. So my Cartesian coordinates here would be simply x squared plus y squared, and that'll equal 1 minus y in parentheses squared. So here is a solution here for one example, converting, looks like polar to Cartesian coordinates. And let's double check here how we made out. Yeah, I guess so. So I guess we could kind of look at it this way, and that's fine. Okay, let's look at some more examples now. Here's another example. They give us a Cartesian equation of 1 over, or I should say, our polar, sine theta minus cosine theta. Here's a polar equation. We're going to take a look to see what this equals, or what this is equivalent to in rectangle coordinates. So r here will be 1 over this sine theta minus cosine theta here. And we're going to multiply both sides again by this sine theta minus cosine theta. So I'm going to multiply by sine theta minus cosine theta. So now I get sine theta minus cosine theta times r. We get our cancellation here, and that's 1. So if we distribute r here, when we multiply, we get r sine theta minus r cosine theta, and this equals 1. Here's a variable. Here's another variable. So this is my y, and this is my x. I now have y minus x is 1. What I can do is translate here, translate this x, and I get y equal to x plus 1. Here's a Cartesian coordinate representation of this particular polar curve. Another example. R squared is tangent theta. If we recognize that, let's say here, let's undo, r squared replaced with x squared plus y squared. Let's also recognize that tangent theta is y over x. Let's go back. So we simply obtain x squared plus y squared is y over x. It looks like we've actually done this one before, so let's guess here it's in this review. That's fine. Let's move on to some of these others. We have this polar curve being r equals 1 plus cosine theta. So for this example, what we're going to do really is we're going to multiply both sides by r. So I'm going to start with this equation. R is 1 plus cosine theta. And you multiply by r to both sides here. So we get r squared becomes r plus r cosine theta. Like the last example, r squared we replace with x squared plus y squared. R cosine theta, like the last example, we're going to replace with just the variable x. So what we end up with is x squared plus y squared is r plus x. Now, translate my x. And notice what we just did here. What I've been saying all along is to try to solve this for r. Now, solving this for r here, we're in a good spot because I could now say to you, all you want to do now is square both sides now. The benefit of squaring both sides will give you, on the right side, x squared plus y squared. So, we have x squared plus y squared minus x in parentheses squared simply becomes x squared plus y squared. You know, or sometimes we see this as x squared plus y squared is x squared plus y squared minus x to the second power. And this is going to be a big deal for us later on. So we just wrote this in rectangular form when it was originally given in polar form. So let me kind of that's a minus x here. Let's be clear there. Okay, let's continue with a few more here for us. And we have this equation here. Maybe they give us r equals, let's say 4 secant theta. Now maybe we've seen this before, maybe not. It looks a little familiar. I'm going to replace my secant theta here now. Let's write this down. Let's do the work. I'll replace secant theta with 1 over cosine. So we get now r being 4 over cosine theta. We're going to multiply both sides by cosine theta. We'll get really r cosine theta is 4. And if you recognize this here, r cosine theta, that variable is x. Sure enough, you get x is 4. Looks like a vertical line. We've seen this one. Now compare this situation here to the following example. What if they give secant theta here is 2? Notice there is no r. So we have no r variable here. Okay? Let's see what we can do. If I use the fact that secant theta here, without the variable r, secant theta is really 1 over cosine theta, and that whole thing will equal 2. I can actually solve for cosine theta. This means cosine theta is 1/2. So cosine theta being 1/2, that tells me that theta has to be two values, plus and minus pi over 3. So in one case, if theta is positive pi over 3, cosine theta is 1/2. In the other case, if theta is minus pi over 3, cosine theta is also 1/2 again. So if we remember correctly, that these here, and I wrote down this fact earlier, if theta is a constant, that's a line through the pole. So if we add here, a photo here, let's see. Well, not this one. Let's remember, I wonder if it'll work. If I paste this, sure enough, it does work. Okay. Well, it's not working like we want, but that's okay. Let's consider this. Theta is pi over 3. That's an angle. So I want to point out this important detail for us. We said those are lines through the pole because there is no r value. Remember, r is arbitrary. You can use any value for r. So I'll write down any r. Theta being pi over 3, what that means is pi over 3, if we double check, that's 60 degrees. Earlier we discussed that this here was a line, pi over 3. That's a line now. It's linear through the pole. And the other line is negative pi over 3, so that's minus 60 degrees. So here's the other line, really. Sorry. There we go. Okay. Let's get rid of this. And what you see here, this is negative pi over 3. If we rotate clockwise, positive pi over 3. Okay, here's my second line. So here's these two solutions here. Just for theta being positive pi over 3 and theta being actually negative pi over 3. Okay, here's my second solution here. Theta is constant. So when theta is constant, we get these lines here. And let me actually be a little bit more consistent, and I'm going to paint this here. Let's see if we go, just so you guys remember, that reference angle is pi over 3. That's going counterclockwise. And if you go the other way, negative pi over 3, this is clockwise. So we can describe it this way. And we get two lines. If you want, call this line 1 and line 2. Now that's what's going on with theta being constant. However, let's also know that we have another fact, and here's the fact that we want to write down. That tangent theta is y over x. This is what we're going to use to convert to rectangular. So, in one case, we're going to actually plug in, we're going to say here that tangent theta is y over x. We're going to plug in the value here of theta being pi over 3. And in the other case, we have tangent theta being y over x. We'll plug in the value of theta here being minus pi over 3. So we're going to use these values here for theta. That's going to get us to where we need to go in terms of rectangular coordinates. Okay, so if you ever have a constant value theta here, yes, they're lines through the pole. We've seen that earlier. But we can get the actual equation in terms of rectangular coordinates with these variables here, x and y, just by knowing theta. And that's the idea. So if we continue this work, let's do this down here, and we'll say that tangent theta now are simply tangent of pi over 3 is y over x, and tangent of minus pi over 3. Let's write it a little better here. This is also y over x. Now you're going to have to know what tangent pi over 3 is. Okay, so if I do every detail, which is not a bad idea, 60, 60, 60, right angle, 1, 2, and this is going to be here, square root of 3. Okay, now pi over 3, 180 over 3 is 60. What that means for us is my tangent pi over 3 here will be tangent 60. Definition is opposite over adjacent. Replace this with simply the square root of 3. I want to point out a detail here. Tangent here, we have that negative value. If you remember, I can pull out that value and say this is minus tangent pi over 3 y over x, because tangent is an odd function. Tangent's odd. There's a nice property. I'm going to replace tangent pi over 3 with the square root of 3. Here's what we have. The square root of 3 in one case is y over x. And if we write it all down here, we have minus square root of 3 in the other case is y over x. And we could solve both sides here for y by multiplying x to both sides. You get cancellation here. Here's what you end up with. Y being the square root of 3x and y being minus the square root of 3x. These are two rectangular coordinate equations. This is what you have up here. Notice this equation here has a positive slope. This has a negative slope. And they go through the origin. So what I can say here is, let me erase this. In purple, we got pi over 3 minus pi over 3. Those are our, let's do this here. Those are our two angles. L1 is y equals the square root of 3x and line 2 is y is minus the square root of 3x. So you got two versions here. Theta is pi over 3. Theta is minus pi over 3. Polar and rectangular.